Kosovichev here to give this seminar, and he did his PhD in Moscow, then he was a postdoc at Cambridge, and now he's at Stanford, and he's going to tell us how we can find out about the interior of the sun by measuring seismology.
Well, thank you. It's a great pleasure of being here, and Argit is a great place to science, and particularly that we have a terrific program on solar dynamo. And actually, heliosismology is one of the motivations of heliosismology is to understand how magnetic field is generated inside the sun, because it's one of the fundamental processes that we don't understand. And so that we are trying to look to develop computational techniques to look inside the sun and just to get some basic understanding. So I'll briefly review the status of dynamo problem, because that's the main motivation. Then I describe what we call global and local heliosismology and how we measure rotation inside the sun, measure flows, and we look also at formation of sunspots, active regions and solar flares. So that's a lot of material here. So let's know how much time I will have. So that's a movie from Galileo. You know that this telescope is now at the Nobel Museum in Stockholm, so you can look at this. So when he built this telescope, he looked at the sun and he saw sunspots. So he observed every day. So that's just one solar rotation here on this movie. So we observe sunspots in that, and we still don't understand the origin of sunspots. So people were looking for a number of years. So Galileo started here. And then you can see now we have for 400 years that we have observed sunspots, and this is kind of people found periodicity, quasi-periodicity, 11-year cycle. And what was puzzling here that when Galileo started observation, the cycle was not many observations at the time, but still kind of you can see periodicity. But then a sunspot disappeared for 50 years. And that is called mountain minimum, and people try to relate this to temperature, because when sunspot was low, there was some correlation with little ice age, and it's here the puzzle. So this is called mountain minimum, and we didn't have these things there, so we don't know what light happens, and if it happens again, because if it happens, then you can see the picture is not very pleasant in Europe, because it's quite cold. So that's. And what's interesting about sunspots, that they appear at the beginning of the cycle, they appear at high latitude. So this picture shows time and latitude. The equator is here in the middle. So sunspot appears at mid-latitudes, and then the formation zone of sunspot migrates towards the equator. You can see the butterfly diagram. When they reach the equator, this zone, then sunspot disappears, and then new cycle starts. So it's pretty regular. Even if you look at the pictures of the sun, sunspots look random. They appear randomly on the surface. But if you make this picture for a long time, you can see this pattern. So now we have magnetic field observations for the last 3 cycles. We have the measurements of sunspot for 20 cycles, and magnetic field only for 3 cycles. So here you can see 2 different polarities, and again butterfly diagram. And that basically the main picture we are trying to understand why these sunspots they appear randomly on the solar surface. They form butterfly diagram, and here you can see also an interesting phenomenon, magnetic field. So they appear bipolar region sunspots. A magnetic field of the fallen polarity is transported. It migrates towards the poles and reverses polarity of the polar field. So the polarity reversals every 11 years around the solar maximum. When the sunspot number is maximum, the polarity changes sign. So it's also part of why magnetic field is transported to polar regions reverse polarity, and that's make solar cycle. So what the theorist develops different models of solar cycle, and one of the ideas is called a flux transport dynamo. And here you can see that originally, if suppose we have a dipolar magnetic field, it's called colloidal magnetic field, and then differential rotation of the sun, equator of the sun, solar equator rotates faster than poles, it will stretch magnetic field lines and generate toroidal magnetic field. Somewhere below the surface, we don't see this process on the surface. And then, when magnetic field is sufficiently strong, it will erupt because of some instability and appear on the surface in form of active regions. So then these active regions decay on the surface, and for some reason that it's probably the weakest point here, that the magnetic field of the fallen polarity is transported to polar regions and reduces global field. Probably it's done by meridional flows. That's what one of the models suggests. It's called flux transport. So once you reverse and reconnect the magnetic field, you come back to again to the poloidal magnetic field of opposite polarity, and then differential rotation stretches it again. So that's a schematic picture. It's actually the best of our understanding how the solar cycle works on the sun. So here basic ingredients of the dynamo model. So what, as I mentioned, it's a differential rotation. It's called omega effect in dynamo theory. And differential rotation generates, starts from poloidal field, generates toroidal field. And then to generate, we need to generate again poloidal field. This is done by helical turbulence. It's called alpha effect. Somewhere in the convection zone. So you twist magnetic field lines, so change orientation from toroidal to poloidal, and connect magnetic field lines, and this will make a poloidal field. So that's important ingredients in differential rotation and meridional flows here in this case, because we need to reverse polarities of polar field. So that's, I also can put this on a computer and calculate models. And here you can see the butterfly diagram produced by this model. They are symmetrical, and they look very similar. They resemble observations, except when you start looking at details here, because as I mentioned, that the magnetic field is transported by, they appear in bipolar regions and transported on the fallen polarity. And here in these models, it's ignored. So we just reproduce the basic structure of axisymmetrical magnetic field. Also, this model was developed to some degree of sophistication and with some attempts to predict the next solar cycle. So here you can see that some previous solar cycles, that's the number of sunspots, function of time, and was attempt to calibrate this model. So you first predict the previous models, you calibrate parameters of the model and predict the following cycle. So it's a future cycle, which is just starting. So that's a prediction of this cycle. Also, they try to take into account changes of meridional flows, because heliosismology found this effect, which I show later. So now how this prediction, so this official prediction from NASA website, and at the beginning it was a prediction in 2007, it was prediction of big solar cycle, and also model predicted big solar cycle. And then now we can see how this prediction evolved with time. So in December 2007, the cycle had not started yet, and prediction changes. Its temperature decreases. Then you can see it decreases further in October 2008. And then they had to change scale because the cycle in May 2000, this year didn't start yet, so it was minimum, and now it's significantly smaller. And then they slightly increased prediction, despite the cycle is still lower. That's the actual observation of sunspot number. The reason for this is because NASA has a panel that decides on future prediction. And this actually, it's extremely important for planning, say, future missions. Extremely important to have prediction of this, because the state of solar atmosphere depends on solar activity, irradiation from the sun. And that's, NASA estimates the prediction, the price tag for prediction of solar cycle is $2 billion. So it's something really important. But the best prediction we have so far, it came from geomagnetic observations. It was a Russian scientist Toll, and he noticed that geomagnetic indices, the minima geomagnetic indices, they correspond to the following maximum of the sunspot number. It's kind of a paradox, why geomagnetic indices would predict the solar cycle. So explanation for this is came from realization that the solar wind during solar solar minima comes from polar regions. So polar regions, they predict the magnetic field in polar regions. It corresponds to the toroidal field generated by the differential rotation, like dynamo models predict. And what we know, we have observations also for 3 cycles at Stanford, Wilkersall Observatory. And the polar magnetic field, the amplitude of polar magnetic field was decreasing with time. So we expect now really, because of this, expect the next solar cycle will be weak. So that's a prediction based on these measurements of polar magnetic field. So polar magnetic field will tells us about the future solar cycle, because it's active regions are generated by stretching magnetic field line by differential rotation. So that's an illustration of our understanding of solar dynamo. So now we have trying to make continuous observations on the sun. It was a solar dynamic, solar heliospheric observatory. It's a European and NASA mission. It operates since 1996 and makes continuous images of the sun. So I want to show you the current image. It's taken this morning. I don't find some spots here. And but if you look at magnetic field, you can see magnetic field appears. So it appears at high latitudes. It should appear with the solar cycle, but it didn't form sunspots. It was big to make sunspots. So this is,
what's the difference between these white and black spots?
Oh, that's two different polarities.
Yeah.
So we measure line of sight, so that's a Zeeman effect. We measure in circular polarization. We measure the signal circular polarization, and that tells us about line of sight magnetic field. And that's 2 different directions of magnetic field.
Or whether they come in or out?
Yes, yeah, exactly. The form loop. Yeah. You can see this loop if you look at UV images. It's, so that's an image taken in helium 304 lines. So that's a UV image of the sun, and also the satellite map images in extreme ultraviolet. Here you can see loops very clearly. And this is 2 million degree plasma of solar corona. You can see that the emerging region will appear soon because sun rotates from left to right. And here it's also this observatory takes images of the solar wind. You can see it was very quiet. You notice only some small activity of some small ejections, mass ejections. So this is obtained by observing in white light. This is Thomson scattering of the white solar light on electrons. So this is a movie that shows the evolution of magnetic field in the past months. So there were some spots. So it looks like a Galileo movie now. You can see some spots appearing and disappearing. So it was in the past months, past rotation, solar rotation, evolution of, and then it's nothing. So the sun is not very active, and so but we'd like to understand what's happening inside the sun, how magnetic field is generated, and if the next solar cycle will be strong or weak. Also, in addition to these space observatories, it's also ground-based networks, because for heliosynthesis models it's very important to have a very long time series, uninterrupted observations. And that was one series of networks around the globe, also trying to make a long time series of solar oscillations. So this is how solar oscillations look like. If you measure Doppler velocity, Doppler shift in some spectral line, then you can see there's some flickering in Doppler velocity. You can see stationary pattern. There's a convection, large-scale convection, supergranulation. And if you just zoom on central part, then you can see some randomly excited acoustic waves. So this oscillation with different colors, they correspond to motions of the solar surface, up and down motions of the solar surface. So it's a Doppler shift of the spectral line. So oscillations are stochastically excited by turbulent convection, and you just need to extract some signal from noise to measure properties of this oscillation. So it's kind of an interesting and challenging task how to use this data, randomly excited oscillations, to measure internal properties. So here it's a schematic picture of the sun. You probably all know that there's some energy generating core. Then energy is transported by radiation up to about 70% of solar radius. And the top 30% is the convection zone, where energy is transported by convection, where magnetic field is generated. So the heliosysmology can consider different questions: the chemical composition, thermodynamic conditions of the sun, determine internal rotation, linear circulation, structure of solar convection, and then we're trying to look for source of solar magnetic field and how the effective fringe sound supposed to form, because all happens below the surface. And also we try to look at some cause of activity on the surface, like solar flares. We don't know why magnetic field gets reconnected and produces solar flares. So the excitation, the physics of excitation of solar oscillations, it's basically well understood. So the solar convection, it makes granules on the solar surface. So material comes up in the middle of granules and goes down at the edges, and velocities, and also convection is different from convection Earth conditions because it's driven from the surface. It's very high velocities at the boundaries of granules. And these downdrafts, these strong downdrafts in the granular spaces, they actually produce acoustic oscillations. So this has been observed just by looking at details of acoustic power in convection. So it's different from earthquakes, but sometimes we can see events, solar flares, that actually can provide a single impulse. So this movie is enhanced, the signal is in fact it's big, but here was a solar flare. It's a movie in the Doppler shift. It's the Doppler velocity here, and you can see some constant Doppler shift in magnetic field, some downflows in magnetic field, and a flare here, and this flare produced a strong signal on the surface, like explosion. And this explosion generated sunquake. So these events are not frequent, so we don't use heliosysmology, but it relates to very interesting physics. So there are two sources of solar oscillations on the sun: stochastic oscillations and also the solar flares. And actually looking at these ripples excited by solar flares, it's interesting for understanding the physics, because you can see ripples like ripples on water. And if you can make a diagram, you can average signal of a circle and plot as a function of time and distance. And then you can see the signal corresponding to a lot of noise around, because it's stochastic waves here. So you can see this ridge corresponding to a sunquake. That's ripples on the solar surface. And you can notice that the slope of this, so it's time, and this is distance, the slope changes its distance. So it means that the ripples propagate faster with time, so they accelerate. So the velocity changes from 10 kilometers per second at the beginning to 100 kilometers per second. And this is different from, of course, water waves, which propagate at constant speed. So the reason for this is because this wave accelerates, because it doesn't propagate along the surface. This wave actually propagates below the solar surface and then come back. And so that's excitation, that's calculations of ray passes from point source to the solar surface. So the waves propagate in all directions from point source, and they propagate through the interior and come back, because the sound speed increases with depth. So that's refraction and the total reflection here, and the waves come back. And what we observed on the surface, we observed just these waves, they come through the interior, in fact, these wave packets. So that explains, if you do calculations, it will perfectly match the signal from sunquakes, the speed of sunquakes, and that also explains the basic principle of heliosysmology. The waves are excited by stochastic sources or point sources on the surface, and then the waves propagate through the interior, and if you measure the travel times, the travel time would be sensitive to condition along the ray path. So just measure the signal, the travel times for different distances, and then you can use some principles of acoustics and deduce properties along these wave passes. So that's again this illustration of the same of how the waves propagate inside the sun. So that you can see they go around these waves and they actually form resonant patterns, because the waves become captured inside the sun for two reasons. One reason is because sound speed increases with depth, and then the propagation depth depends on takeoff angle and the sound speed profile. So this point corresponds to a point where the local sound speed is equal to horizontal wave speed, phase speed of acoustic waves. And also they're reflected from the surface because of very steep density gradient at the surface in the photosphere. So that's they form a resonant cavity. And because of these, the waves, they form some stationary patterns, resonant modes, and you can measure frequencies of these modes in addition to travel times. So that's these two basic techniques of heliosseismology. So you can take one of the movies that I showed, acoustic oscillations. So I measure Doppler shift over the whole disk, and then you just do Fourier transform in space and time. So usually we use spherical harmonics decomposed in space, and then we do Fourier transform in time of the coefficient of spherical harmonics, and if you plot the power spectrum, so it's a frequency, and this is angular degree of spherical harmonics, you can see the power spectrum. You can see these very nice ridges of standing waves, standing acoustic waves, they are trapped below the solar surface. And they're exactly stochastically. So these frequencies, 3 MHz, correspond to the period of 5 minutes. So that's a characteristic period of acoustic waves in the sun. In fact, here the lowest reach, it corresponds to surface gravity wave. It's like ocean wave on the solar surface. And these are just resonant acoustic harmonics of a different radial order with different number of nodes along the radius. And the second approach is to how we measure the travel times when we don't have a point source. So we calculate cross covariance of the signals. So we take 2 points on the solar surface and we measure the signal, associated signal function of time and position, and then we'll measure 2 different positions at a distance delta, and then we calculate cross covariance with some time lag tau. So we take sufficiently long time series, say for 8 hours, and we calculate cross covariance function and plot the function of distance between these points and the function of lag time, and then we have these ridges. It's a time distance diagram. In fact, this is the lowest ridge. It can show the same acceleration with distance as the flare ripples. And these ridges are created by multiple bounces below the surface. And so that's 2 basic. So then you can use this to measure travel times. You just fit some model here of wave packet and determine phase and group travel times, and here determine eigenfrequencies of normal modes. So let me show you theoretical spectrum of solar oscillations. Then you can actually use solar model and calculate the spectrum of solar oscillations and compare with observations and see what the differences. So we try to plot the differences. So here is the total spectrum of solar oscillations. It consists of acoustic waves and also internal gravity waves, they call G modes, and surface gravity wave, it's F mode. So far we observed only this part of the spectrum. There were some attempts to observe the internal gravity wave because they are very sensitive to conditions in the solar core, but so far it wasn't conclusive, so there was no data here. So we just look with acoustic waves and surface gravity waves. So usually, normally we compute the frequencies taking very long time series, like 108 days or 72 days, and it gives a very accurate measurements of oscillation frequencies. Here you can see the same spectrum, same ridges corresponding to normal modes, and here the error bars correspond to 1000 sigma error bars. These are some of the most accurate measurements in astrophysics. We don't know gravity constant to the precision we know the associated frequencies. So it's a very, very accurate measurements. And for the second technique, what we call local teleseismology from travel times, here we measure the shifts of travel times for different positions and then relate to perturbations of sound speed and flows. Flow speed below the surface is just a advection effect, and this is a change because the sound speed changes. And then we separate this effect by measuring signal, reciprocal signals between points A and B, say, and take the difference of these measurements. Then we the difference will be sensitive just to flows. And if you take the mean value, then we cancel second term and it changes to the sound speed along these. So then we do tomography and solve the reverse problem to determine these variations. Three-dimensional images of sound speed and flow velocities. So what the current status?
Gravity wave, I mean, it's a matter wave, matter propagating, or what do you mean by gravity waves?
Oh, the gravity, no, that's internal gravity waves, that's a buoyancy waves. So we have two types of gravity waves. It's a surface gravity wave, like ocean wave. So they're just
it's matter that propagates. How do you see a gravity wave?
We see on the surface gravity wave, we see by looking at Doppler shift, displacement of the surface. The same way we can see acoustic waves by measuring a Doppler shift of spectral line at this form of the surface. And Doppler shift tells us about displacement. So we measure like
it's the space-time that has a wave.
How we know that this is
no, that is a confusion.
Not gravitational waves.
Yes.
Yeah, gravity, not gravitation. You mean really that the space-time is...
Yeah, that was what I showed here.
No, gravity waves has nothing to do with gravitational waves.
It's not gravitational waves. It's a buoyancy wave, gravity wave, called internal gravity wave. It's driven by buoyancy force. Restoring force is buoyancy.
And they are seen in meteorology.
The pointing vector, which is changing.
Oh, the pointing vector, yeah, pointing vector for these waves, it's a bit complicated. Because they have the group velocity and phase velocity, they're not in the same direction.
But this internal gravity waves propagate only in a status to the flights.
They propagate only in radius area.
Yeah.
But they still this the signal of this wave because they're trapped in even deeper inside the sun, but still they cause displacement of external waves. So we still can see, in principle, signal is very weak. That's why we have probabilities. But in principle, it's but this has nothing to do with gravitational waves. It's the restoring force, the buoyancy force.
But they are not like electromagnetic waves.
No, they're not electromagnetic waves. That's all pure thermodynamic waves.
No, but in electromagnetic, you see that the electric field changes. That's the way it propagates. Here, what is the corresponding to the electric field?
So here, that's what is corresponding here in acoustic waves. It's just a compression. It's driven by pressure. And what is moving here, the particles move in the waves. So we look at the motions of particles. And the same in gravity waves. It's in internal gravity waves. They're driven by buoyancy, and we also see motions of particles here.
So the quantity that changes is the entropy perturbation.
Is what?
Entropy perturbation. That's one quantity, and the other one is the vertical velocity.
No,
so with this you get a wave
they're
equation.
almost these waves are diabatic, so that's.
Yeah, but is I said perturbation. So the
perturbations are diabatic, and it's like.
yeah, but if there's a displacement because the background entropy changes, the perturbation relative to the varying background changes.
Yeah, that's why they have some particular frequencies here. So let me now briefly show some results. So here it's an internal rotation of the sun is deduced from the frequencies, and how it's measured. The frequencies of these standing waves, they depend on the sound speed profile, and depend also on rotation, and the waves they propagate in the same direction as rotation, that they have high frequencies, and the waves they propagate in the opposite direction, and this is called frequency splitting. So by measuring frequency splitting, we can deduce internal rotation inside the sun. So here that's the pictures obtained by different inversion techniques, and here you can see lines of constant rotation inside the sun. This is a base of the convection zone, and the gray area shows where we are not sure about inversion results. And you can see that rotation, it was known since Galileo that equator rotates faster than the higher latitudes. And here we can see the differential rotation, it persists through the whole convection zone, and then radiative interior, it probably rotates uniformly like a solid body. So that's the explanation for this. Some models now differential rotation, they explain this as interaction between convection and rotation. So that causes acceleration of the equator inside the sun in the convection zone. And you can see a lot of details here. You can see also that some shear layer below the surface. The origin of this shear layer is not well understood. And also that shear layer at the boundary between radiative zone and convection zone is called tachocline. And some dynamo theorists, they believe that magnetic field is generated in this layer between radiative and convection zone, and magnetic field is so generated by the shear layer, by the stretching, by differential rotation, and the storage occurs below the convection zone, because it's the convection zone would convection would bring magnetic field immediately to the surface, and they argue that magnetic field must be stored below the convection zone in tachocline. So that's a picture of differential rotation, and actually this parameter, differential rotation, is used by dynamo theorists. It's one of the important input parameters. And also some discussions of its polar jets here, and also you can see some evidence for rapid change of rotation near the polar regions by here technology. And I mentioned the models, now it's numerical models, three-dimensional models of convection and in rotating envelope. And they can reproduce differential rotation, but the shape is a bit different. So models usually they produce rotation constant on cylinders, and it's not quite what is observed. But this is getting improved now, so it gets more understanding of how to improve these models, which will differ from boundary conditions here, the rotation law in these models. So essentially physics is understood. What was puzzling about the internal rotation, that we can see some zonal flows. We can see some bands of fast and slow rotation. And these zonal flows, they're not very strong. So rotation speed of the sun is 2 kilometers per second on the surface, and in these flows, zonal flows, the speed is about 8 meters per second. So they're quite weak, but they're very persistent and very, very noticeable on the surface. So they call torsion oscillations for historical reasons. And if you make a picture, if you plot these flows, amplitude is these flows as a function of time. So we have data from 96 and function of latitude. Then you can see the zonal flows that yellow rotation is faster and blue rotation is slower than average. And you can see they immigrate, the zonal flows immigrate towards the equator. And what is puzzling here, that magnetic field appears at the boundaries, between this boundary, between zones of, now the boundary of zone of fast rotation, with a shear layer here. Also you can see change of in polar regions of rotation rate, which we also don't know how to explain. And here interesting feature that we see already zone flows that would correspond to the future solar cycle. It's already appears at high latitude, so magnetic field would appear somewhere at the boundaries of these flows. It's just such appearing. So probably these flows are induced by magnetic field below the surface, and then amplitude these flows would depend on magnetic field conditions below the surface. But we have not made a connection between the internal magnetic field and the flow speed. So this is one of the most important results of helix seismology. Also, we can look how these flows change with depth. And there's some evidence that they actually don't penetrate these flows, donor flows. They're not measured at the base of the convection zone, where dynamo series predict magnetic field is generated. So they're mostly concentrated just below the surface. And for some reason, they're stronger in polar regions, and stronger and deeper. So some attempts to measure variations of internal rotation at this transition layer between radiative zone and the convection zone, Tahat line, with time. So this is variations of rotation rate. That's two different instruments from space, so NDI and also GONG ground-based network. So they try to find 11-year periodicity in change in rotation rate, because if magnetic field is generated in the Tahat line, the bottom of the convection zone, one would expect to see also variations of internal rotation, because magnetic field will change convective properties, and that will change differential rotation because it's maintained by convection. And it must be non-linear phenomenon, because we know the solar cycle is non-linear, so one would expect some strong changes in rotation rate, but we don't see this. And these are fluctuations, and there was some evidence first that people thought maybe some periodicity here, and then it kind of disappeared. So it's resulting in inconclusive. But it's quite important that maybe a solar dynamo is not located in what we call Tahat line. So that was actually called paradigm shift. Maybe it's somewhere close to the surface. We're still learning how to do measurements, because it's very challenging to measure flows and sound speed variations that deep inside the sun, particularly from travel times. So here's some attempt. So what we do, we usually use artificial data. So we take a solar model and generate random acoustic waves in computer, and then try to apply our techniques and to see how well we can actually recover these features. So that's kind of attempt to measure some small sound speed variations inside the sun. And these signals are extremely small. It's very difficult to measure. And then we can apply to real data and see if we can notice some changes also in structure in this layer, traditional layer. So by measuring travel times, as I mentioned, that we can actually get the three-dimensional flow maps below the surface. And these are quite detailed. I just show. So this is how we do this inversion procedure. So we have these ray passes, and then we have a three-dimensional grid, and we measure travel times for different distances, and then also shift this central point on the surface, and then we get recovered by these rays, acoustic rays, at some region of the sun, and then solve inverse problem on this grid. So this is an example. If you look carefully here, you can see some small arrows here. So that's a magnetic field map. These two colors show two different polarities. Again, line of sight magnetic field measured from Riemann splitting of the solar surface with regions of sunspots. So magnetic field is quite structured here. And we can measure the flow velocities below the surface. Here you can see some convective cells we call supergranulation. And so we can try to analyze these maps. So it's only small portion of the sun. So we have a lot of now data about subsurface flows and evolution of these. And we're trying to learn how to relate to magnetic field, these flows. If you just average over some regions, then you get large-scale flows. So here this map shows the flows 2,000 kilometers below the surface. And this average over some large region, so these are large-scale flows deduced from these detailed maps. So again, you can see magnetic field with two different colors, and you can see some large-scale circulation below the surface of the sun. And particularly what was found is that around active regions you can see large-scale convergent flows. So magnetic field somehow it generates convergent flows So that's probably one of the reasons why we have some spots, these converging flows. And they change transport of magnetic field of the sun. So it's quite a complicated process. So here it's obtained by a different technique when you can measure the local dispersion relation of the waves and also find the flow maps, and they're quite similar. So then what we do, we take these flow maps and we can measure meridional circulation just by taking north-south component and averaging over longitude that will give meridional circulation
Excuse me,
flow.
I'm interested in symmetry with respect to the.
It's not symmetry
Yes,
here.
yes.
Yes, with respect to
So,
the equator.
is there any flow passing through the equator to, from south to north or north to south?
Yeah, there's a lot of flows that pass through the equator. So it's, but if you take, it depends on the scale of these flows, because you have convection flows, you have convective cells everywhere, so that the flows passing through. But if you look at just the one particular component, which is called meridional circulation, and meridional circulation definition for this, we take north-south component and average over longitude. So then we'll have only flow that is asymmetrical component in this direction. So I'm going to show it here. So here you can see here particular measurements of these flows in 1996, and you can see this flow was 20 meters per second. Here it's equator, and was flow from equator to North Pole, and here flow from equator to South Pole, and you can see that in the equator is zero, it's meridional flow. And it actually stays zero, this asymmetrical component. With some precision, of course, so it's not absolute. But here what's interesting that this flow, this corresponds to these large circulation cells from equator to the poles. It's a very narrow flow. It evolves with time, and dynamo theories, they believe that this flow is responsible for transporting magnetic flux to polar regions and reversing polarity. So what by heliosysmology we are able to confirm this. But we have not seen yet reverse flow, because if you have flow from equator to the polar region, it must go somewhere inside the sun and come back, so the circulation cell. We have not seen reverse flow. It's very weak, it's only 20 meters per second from the surface. Just below the surface it becomes much weaker, deeper down, it's difficult to measure.
And these flows has radial motions or not? Radial component.
This is only horizontal. This measurement is horizontal. Yes, no, we have not measured vertical for these flows. It's much more difficult. But it looks systematic, so that it's measured by different techniques, heliosymology techniques, and we can see systematic flow from equator to the polar region. But it evolves with time. It changes the solar cycle. Particularly it becomes weaker when the cycle started with the solar minimum, previous solar minimum 96, 97. And then when new magnetic activity appeared, it affected this flow. So magnetic field that appears, emerges from the interior, it also changes the flow structure. So this is probably important result for solar dynamo. But solar dynamo, the dynamo model, they don't predict meridional flow, they take also the input. They are kinematic, so the dynamo model, they take flow field and then they predict magnetic field. But it's, apparently it's important to look at back reaction of this. So why this happens? Why meridional flow changes with time? So if you look at detail these flow maps, you can notice that some converging flows around active regions. And they mostly converge around leading polarities somehow. So this you can see bipolar magnetic field. The structure is complicated, but on average you can see the red polarity is leading polarity and blue is falling polarity. And then the blue polarity is actually transported to high latitudes, to polar regions, and these magnetic fields will reverse polarity. But this flow is mostly concentrated where that's in the leading polarity. In fact, some spots, most concentrated field is the leading polarity, and falling polarity is more diffuse. In many cases, you don't see some spores in opposite polarity, just it's bipolar groups, so you can see loops here, but some spores concentrate magnetic field usually only in front. So that's probably what the reason for changing the mean meridian flow patterns. There's a generation of large-scale converging flows around the polarities. And that would explain why only the polar polarity is transported to polar regions.
But these regions with a very strong magnetic field, the strong magnetic field should suppress motion perpendicular to magnetic field.
No, that's this large-scale pattern outside magnetic field. So you can see it's a large scale, much larger than, I'm not talking about inside transport.
Okay.
So also what we have not measured yet in heliosysmology, it's actually the polar regions are difficult to see because the sun, its inclination angle is only 7 degrees relative to ecliptic. So we don't see polar regions. We cannot have a spacecraft to fly outside ecliptic, so it's just a white area. We don't know what's happening in polar regions. It's very difficult to measure. So we try to use some high resolution observations. It was a Hinode spacecraft. It's a Japanese spacecraft. It's a big telescope, largest telescope in space, and they can point in near the polar regions, so that the whole field of view of this telescope is just this small area. But because of high resolution, we can try to get some information despite foreshortening in this region. And here I show that how we use these polar regions from the spacecraft. And that's the measurements of large-scale convection in near polar regions. And again, if you calculate meridional flow here, so that's the meridional flow. You can see the measurements are very noisy. Here is only 16 hours of data. So here it was equator, and that's the flow towards the South Pole, and here that was to get from Hinode spacecraft, so that you can see meridional flow continues, and I'm not sure if it changes sign near polar regions or not, so we try to continue this observation and to learn about dynamics of polar regions, because it's important for dynamo theory to know. And what's interesting is the same spacecraft, it looked at magnetic field in polar regions, and we found that magnetic field is very structured. In dynamo series, it's just a uniform magnetic field, and it changes polarity every 11 years, large-scale magnetic field. But it turns out that magnetic field consists of just elements, very small, tiny elements with scalar Gauss magnetic field strengths. And how we change polarities of this field is all single polarity here in polar regions. How we do this, it's a big puzzle. Because that's something that small-scale structures are organized on kind of on a much larger scale. So let me now show briefly about sunspots. So this is a movie of sunspot. It's taken by a ground telescope. I think it's a Dutch open telescope. You can see it's umbra and umbra. There's a granulation here. And one of the puzzles in solar physics is why magnetic field gets concentrated. We have a turbulent medium, we have convection, but still magnetic field tends to be concentrated in these tiny sunspots. It's several kilogauss magnetic field here. It's actually, field strength, it's above the partition level with turbulence here. So what makes this? It's a big puzzle. It's also structure kind of interesting here. So was discussion for some time that how magnetic field could be organized in flux tube, and then above the surface we can see some kind of expanding magnetic field lines. So, but the puzzle was what holds magnetic field lines here. So Parker suggested that it's probably flows. Probably only flows can confine magnetic field. And since, as Sigurd mentioned, that the flows don't propagate across magnetic field lines, that you have to make it structured. So the flows actually flow between these elements, and they provide some hydraulic pressure, and then they will hold these magnetic tubes together. So that's Parker's model, and we look by heliosysmology. I show you a movie. That's a movie of a sunspot from a spacecraft. And that's the actual data we use, so it's around some smaller spots. And then we look by heliosysmology, we look at the sunspeed structure below sunspot. So now I make this upper boundary transparent and show sunspeed distribution below sunspot. Here the different colors show the sunspeed is red where it's greater than average and blue is where it's smaller than average sunspeed. And you can see it's kind of two-layer structure here. And we can see even some connection below surface to smaller sunspots. And now I show the flow pattern below sunspot. So this is symmetrical flow, this is a schematic picture because it's only the symmetrical pattern was extracted here. So indeed we can see some converging flows below sunspots. And maybe some diverging deeper down. So interpretation of these measurements that the sunspots, they are dark because magnetic field inhibits convection. It stops the heat transport. So that's, the temperature is much lower here. So we use this from surface measurement. And this area, where the cool area continues to about the depth of 3,000–4,000 kilometers below the surface. And then it's somehow replaced by that's water material, probably some accumulation of heat flux here in this region. But the reason that with these measurements of the flow pattern, they correspond quite well to the Parker's idea of converging flows below sunspots. We don't yet quite sure that what drives these flows, because on the surface we can see also outflows in the filaments, where the filamentary structure is seen outflows, it's ever shaded here. So we still don't have models of sunspots, and people try to do some numerical simulation. That was one of the models, numerical simulations, that models magnetoconvection. And actually, when they form some localized magnetic structure, they can see convergent flows below the surface. So that's kind of the development of theoretical development of sunspot models that still continues. And in heliosysmology, they're trying to look at more details. This again from Kennedy spacecraft. We try to measure more detailed structure of flow below sunspot, and here again we found similar circulation structure, conversion structure around magnetic field. And here it's more detailed, and because it's a high resolution, we can measure waves with shorter wavelengths and get better spatial resolution by heliosysmology. You can see similar to layer structure and also some kind of filamentary structure. So that was schematic picture of sunspot. That was, as I mentioned, that just below the surface, it's a very thin layer where convective cells are inclined in magnetic field and to generate a mean flow pattern. It's called Evershed effect here. But below the surface, you can see circulation pattern towards the sunspot that actually confines the magnetic field. So that's what we think of. We have more results to show, but here it's actually we look at formation of sunspot, because sunspots we emerge from below the surface. We try to find roots of these. It's images of when sunspots appear on the surface, images of sound speed below the surface. There's nothing. Then it was some structures appear. We try to look at also at what we call emergent magnetic field. So there's some structure in magnetic field emerges below the surface. But we still don't know what the roots, we don't know how deep the roots of sunspots, where actually magnetic field is originated. So I think it's already spent all time. I just wanted to illustrate some more movies. There's emergence of vertical region, you can see magnetic field, and I show some images below the surface, sound speed images, formation of vertical region. So that was a previous active region, and here once we have a significant magnetic flux on the surface, it immediately forms this two-layer structure, and then it amplifies, and then at the end we can see some kind of loop-like structure, but we're not sure again about how deep these roots are. Here the depth of about 40,000 kilometers below the surface, and the depth of the convection zone is 200,000 kilometers. So it's, we cannot learn how to make these images. And also wanted to show you about solar flares very briefly. We know that magnetic field, when it appears on the surface in some spots, at some time magnetic energy got released that produces solar flares. So here was some solar flare in H alpha in 2003. It was actually a big flare. It caused some power outage in Sweden this way in October 2003. And here's measurements of magnetic field from spacecraft. So we measure magnetic field every minute here. And if you look here at this movie, you can see some energy release here. It's actually energy is released usually around neutral line. We have magnetic field of opposite polarities, and structure is extremely complicated. So the flares appears when the magnetic structure is very complicated. All polarities are mixed together at the neutral line, and usually what happens, some kind of process of magnetic field annihilation around neutral line, because here the magnetic field is decreases very rapidly in a matter of minutes, and that probably would cause the energy, magnetic energy converted to energy of particles and high-speed flows, high energy radiation. So here actually you can see some signal here that when flare happened was some kind of discharge here, some connection of these two magnetic polarities. So what I think was some energy release was related to some process of magnetic reconnection around this neutral line. Probably happened somewhere high in the solar atmosphere. These are measurements in low atmosphere. But then we look at the flow patterns, of interest flow patterns below the surface. So it's the same magnetic field, but arrows show the flow pattern. It was a very strong shear flow around neutral line. So we're trying to relate these flow patterns below the surface to energy release in solar flares. And this kind of also interesting direction in Helios cosmology.
You mean there is flow before flare?
No, it was because its resolution here it's 8 hours. You can get a flow map by taking 8-hour integration time to calculate this cross covariance that I showed. And calculate travel times. So I cannot say precisely it was before flare or immediately after, but it was during this period of flare. What's measured. And this pattern was not observed in the previous 8-hour period and not after this 8-hour period. So there might be some evidence for this. So I want to show another flare that was also a similar shear flow during another flare. So also again I wanted to show some more events related to the sun quakes. In solar flares, what we think that energy is actually released somewhere in the corona in low density plasma, and then its reconnection generates particles, high energy particles, and they propagate along magnetic field lines, and they hit the solar atmosphere, or dense atmosphere, generate high pressure region in the low atmosphere, and then it expands this high pressure region. It causes what's called atmospheric evaporation and also shock waves. And these shock waves it actually causes these sunquake events. So we have more observations of these, and what one the puzzling feature was that these events, sunquake events, they appeared on the declining phase of the solar cycle. So somehow these events are related to the solar dynamo because of a lot of solar flares. The first event when we launched a solar spacecraft was in 1996. It was the last flare of the previous solar cycle. And then for a long time we didn't see these sunquake events, and they appeared only in 2002. Why these strong flares didn't produce this effect, we don't know. It's somehow related to magnetic field structure in these flaring regions, the energy release. So somehow this phenomenon is probably related to dynamo. I just wanted to show some movies where you can actually, that's unprocessed movies of Doppler shift You can see flares here, and if you watch carefully, you can see waves, you know, you can see ripples. The previous movie that I showed, it was processed just to make it easier to see these waves, but this is an unprocessed movie. It's just a Doppler shift, and if you watch, you can see these ripples, so it's kind of amazing to see ripples from the sun.
And this is shock waves which arises after flare or what? I mean these waves.
That's after flare, yeah. They form
Yeah, just
20 minutes after
shock
flare. It
waves.
takes about 20 minutes to form this. It's much slower process than the flare itself. So let me now finish my presentations. I wanted to show some more examples, but I'll keep these. So what the future of this? So now we plan to launch the next solar observatory, called Solar Dynamics Observatory. So now this is scheduled on February 3rd, 2010, and it will take. It will continue taking images of the sun in Doppler shift and magnetic field, but with much higher resolution and continuously. Because what we learned from the previous investigation of the sun, that the small-scale structures are quite important. In dynamo series, they actually ignore the small-scale structure. They do what they call scale separation. They prescribe some diffusion coefficients and some what we call alpha effect, and then consider only large scale. But what we learn from Helios's knowledge and looking at magnetic fields, that is probably not true. Because this interaction between different scales in the sun is more complicated. And actually the sun spots themselves, they participate actively in, they're not a product of dynamo, they may participate actively in development of dynamo. So now we'll take images of actually 16 megapixel images of the sun every few seconds in different polarizations to measure magnetic field and Doppler shift, and also in extreme ultraviolet. As images to look at these coronal loops, a tremendous amount of data that we expect, 2 terabytes of data a day to do the whole heliosismology and magnetic field, trying to understand origins of magnetic field and the cause of solar flares. That's some future suggestions that were to make to use 2 spacecraft to probe deeper interior inside the sun. So my conclusion is that heliosismology, it's a very interesting tool, and to look inside the sun, to study flows and structures below the surface. It provides some constraints on dynamo series, tells us about formation of sunspots, and it also tells that maybe subsurface dynamics is important, also for energy release on the surface, and still we don't have basic understanding of this process. We try to learn what's happening, how the sun works. Thank you.
So we already had some questions, but I think we have time for a few more.
I had a question about observations of sun cliffs. You told would observe some cliffs only on decreased space of solar cycle. Maybe it is just selection effect. Because not too much events really was observed.
We didn't observe every flare. I don't know statistics, but it looks like it was not a selection effect, because there's many flares were observed during solar maximum. It's not just. It's possible that some flares were not observed, because in solar spacecraft they didn't have continuous coverage. So, but there was a lot of strong flares here that we did analyze, and they didn't have this effect. So if we just compare the number of flares, then probably maybe something was missing. We don't know, but that's statistically that's what we see events only here, and you see here. That's what we should tell.
What is the accuracy of measurements of velocity field by means of seismology?
It depends on what scale, because we can measure very precisely the rotational velocity, Precision is maybe about meter per second, or a few meters per second precision for rotation, but for smaller scale precision of 100 meters per second around some spots. It depends on what scale and time, averaging time. If the flow is stable, then it measures more precisely. If it's variable, convective, then much less precisely.
You mentioned in passing that one of the most important outcomes from helioseismology was the determination of the time dependence of the solar torsion oscillation.
Yes.
In hindsight, how important do you regard the determination of the core temperature of the Sun? The temperature of the core of the Sun.
Core?
Mm-hmm.
Yeah, it was very important, but it was the original motivation for helioseismology was to actually to solve solar neutrino problem. And helioseismology provided constraints on solar structure, telling that the standard solar model is correct, and then the solution must be in physics, neutrino physics. And so that was a quite important development. But still we can see some differences between standard solar model and sound speed traction. And now it's a lot of discussions about composition of the Sun, because it relates to chemical composition of the Sun. I didn't have time to discuss this, but it's also a hot topic because chemical composition is related to. It's very difficult to determine the composition of heavy elements on the solar surface spectroscopically. There's some uncertainties. We don't know how much oxygen on the Sun or some other elements, heavy elements. And the structure of the core depends on heavy element because it determines the radiative energy transport inside the Sun. So it's quite an important topic, and it's continuing developing. And one of the hope was that if you can measure internal gravity waves, they're very sensitive to structure of the core because they're just trapped there. So there was a lot of effort to discover these gravity waves. Still continues.
More questions?
I can. My question about observed time distance diagram. You show very clear P-modes, but also very clear to see some horizontal fringes. What is it?
Oh, that was because it's a continuation of some of the ridges. It's because the distance of that's the waves they actually travel for more than 180 degrees, and then it's just
This fringes looks very strange.
Yes, yeah. But it's not a physical effect. It's because it's a ridge. They should continue above 180 degrees. But because in this analysis we didn't distinguish this distance from distance less than 180 degrees. It's pure geometrical effect.
I'm not so familiar with observation. And, is it possible using your next satellite to measure 3 components of velocity field? At present, Hinode can only measure the line of sight velocity field. So how about?
Well, that depends on technique, because the line of sight measured from Doppler shift, right? That's a Doppler shift in spectral line, tells about line of sight. And to measure perpendicular velocity, you have to look at something else. You have to look at displacement of some features. Say how that people use the granulation, granules displaced, the light square flows, so magnetic features are displaced. And here we look how the acoustic waves are displayed by these flows. So we use acoustic waves. So we kind of use a Doppler shift for acoustic waves to measure the other components.
You just refer to the possibility of using 2 satellites. At the same time, you can.
Yes, yeah. That's now what, as I mentioned, that we don't know much about solar poles, and it's a project for the next Japanese spacecraft, Solar Sea. It's one of the ideas is to launch spacecraft around the solar poles and to measure what structure of magnetic field and flows in polar regions, and then see how that polarity is reversed there. So it would also provide some data. So from two spacecraft you can focus acoustic waves, you can pick up acoustic waves that are focused somewhere deeper down. Because currently by these techniques, when we measure travel times, we cannot go very deep because the propagation depth it's 1/3 of the distance. So we can determine deep structure only from resonant frequencies, but not by local field technology. In the frequencies are sensitive only to symmetrical components of flows and sound speed. But here, because it's 1/3 of the distance, then it limits the because we see only on the solar disk, the distance is limited. So two spacecraft would solve this problem.
So if there's no further question, let's cover some of it.